Hello everyone, welcome back. In week 2, we have learned about linear algebra, and in this lecture I will implement those concepts that we have learned in linear algebra course using R. So, in this lecture we will start with vectors, we will do vector operations, then we will move into matrices and do matrix operation like multiplication of matrices, calculating the determinant of a matrix, something like that, and eventually we will solve a system of linear equations using matrix algebra, linear algebra. So, let us start with vectors. I will create vectors and then perform vector additions like vector multiplication and all other things that we have learned in linear algebra on vectors. I will show you creation of vector using two functions, one is C, another one is sequence. Both of these you have met earlier in the previous lectures. So, let us start with C function. I want to combine some data to create a vector. So, I have 5 data values 1, 3, 5, 7 and 9. I want to combine them together using the C function. So, that I will create a new variable u as written here in the code, and that u will be a vector, one dimensional list, right. So, if I execute u assigned to C and those values, then u is created. In the environment you can see u has been created. Now, I can print u and you can see it is saying u is a list of 1, 3, 5, 7, 9. So, we can call it as a vector, right. It is a one dimensional list. So, I can call it a vector. Now, apart from C, as we have learned earlier, I can create a vector using the sequence function also, right. So, let us do that. So, what I am doing here in this, I want to create a vector that will start with 12 and it will go up to 46 with an increment of 8, right. That is what we do in sequence function. We give the first value, the lowest value or the first value, and then we give the upper limit and we give the increment, right. So, that is what I have given here. 12 is the first value, 46 is the last value, 8 is the increment. So, let me execute that, and that will give me a v vector because I assigned that to v. So, if I print v, I can see it is starting with 12, then we are adding 8. So, it is becoming 20 and it is going up to 44, because if I add 44 plus 8, it will be on 52, right. So, I cannot go beyond 46. So, it stops at 44. So, I have got two vectors, right. So, I have created these two vectors. You can read a data file and extract vectors also. We have done that earlier. Now, once I have got the vector, one important thing that we have to understand is indexing of vector. What is a vector? If you remember, we have said that vectors are stacked numbers, right. So, now if I have stacked number 10 numbers, 3 numbers or 4 numbers, I should be able to label them. So, in R, label starts from 1 to 2, 3, 4, something like that. So, I may ask that okay, I want the third number in my vector. So, that is the third index, right. So, I should be able to get a particular value having a particular index number to that. So, let us try to do that. So, how we do write it? We write the vector name and then we put the index number or element number. For example, as I have shown in this script, if I have created the u vector few seconds back, if you look here in the console, u is 1, 3, 5, 7, 9. These 5 numbers are stacked. I want to get the third number. What will be the third number? Third number will be 5, right. The first number is 1, second number is 3, the third number is 5. So, I want to get the third number. So, how I should write? I should write it u and in the square bracket I should write that index 3. So, u in square bracket 3 means it tells R that okay, I want the third element of this u vector, and then I am putting it under the print so that I can print it. Let us print that. So, it says 5, obviously because the 5 is the third element or the third number in my vector u. So, this is how you actually use indexing of vector. You may want a part of that vector and do some further calculations. Now, in the lecture on vector and vector operations in the last week, we have learned about addition of vectors and multiplication of vectors. So, let us start with addition. So, addition can be of two types. I may add two vectors, I may add a scalar to a vector also. The simplest one is always the addition of a scalar to a vector. So, suppose I want to add 2 is a scalar value thing, right, to a vector u, to the vector u we have created few minutes back. So, how I do? It will be a simple addition. I have to use the addition operator, the plus sign here. So, u plus 2 will be summation of a vector u and the scalar 2, and it will give me a new vector which I have assigned to p, and then I am printing this. So, let me execute both of them together. So, what I have got? I have got a new vector 3, 5, 7, 9, 11. You can easily see my original vector u has 1, 3, 5, 7, 9. So, if I add 2 to them, the first element will become 3, the second element will become 5, and so on. So, I have done scalar addition. Now, I want to do vector addition, right. I want to add 2 vectors. So, it should be similar. I will add the addition operator here. So, here what I am doing? I have created earlier 2 vectors u and v, and I want to join them. I will sum them together using the addition operator, and I will assign this whole thing to a new vector q, and then in the next line I am asking to print the q. So that I can check what is that vector created by addition. So, that is what we have got. We have got a new vector q with elements or the values 13, 23, 33, 43 and 53. So, we have learned addition. It is very simple to do. Now, we will move into multiplication. Again, just like addition, I can have a scalar multiplication and I can have multiplication between vectors, right. So, start with the scalar one, the simplest one. So, for scalar multiplication, suppose I want to multiply the v vector with 2. So, what I will write? I will write 2 and then I will give this star. The star is the operator for multiplication, if you remember, and then the vector I have written, and I am assigning that because this multiplication will give me another vector. So, I am assigning that vector to a new variable, and then in the next line I am printing a so that I can check it. So, let us execute this. So, I have done the multiplication, scalar multiplication, and let me print it. Okay. My v, if you see, let me expand the console. V is 12, 20, 28 and so on. So, if I multiply by 2, it should become 24, 40, something like that, and that is what has happened here. You can see a is a vector with first element 24, second one is 40 and so on. So, I have performed scalar multiplication. Now, I want to multiply 2 vectors, right, and when it comes to multiplication of 2 vectors, we are talking about here about the dot product, right. So, I want the dot product between 2 vectors. Now, you can do dot product by using the explicit definition how we have defined dot product, and then you can use the base operator and base functions of R to do that. But there is a library of R which is named as geometry library, and that library has a function called dot, and that can do it in one line, the whole calculation of the dot product, right. So, just I have to give the 2 vectors as a argument to this dot function, and it will give me the dot product. So, what I have done here, I have already installed this geometry library. If you do not know how to install, I will just show you briefly. You go to this tool for this R Studio, and then you click on this install package, then it will ask what you want to install. So, you can write here geometry, right, and then you simply click install. I have already installed it, so I will not do anything further. Now, once you have installed a library in R, does not mean that library is now accessible to you while you are working, right. You have to make that library accessible to this session, current session of your work. So, how we do that? For any library, if you have to incorporate in the current session, you have to call that library. So, we call that by using the function library, and then as an argument in the round bracket you have to put the name of the library that you are calling, and then you will use subsequently. So, I want to use the dot function which is part of the geometry library which I have installed earlier. Now, I want to use the dot. So, I have to call the geometry library. So, I am calling geometry library here in this line. So, let me call that, and geometry library is now loaded in this session. So, now what I will do, I will use this dot function to calculate dot product between u and v. So, u and v will be two arguments for this function dot, and if you remember what should I get by the dot product? Do you remember that? I should get a scalar, right. So, it is a scalar product. So, I am assigning that value to b. So, let us perform that dot product. I have done the dot product calculation. Now, I want to print it. It is 860. So, I have shown you how to do simply addition, multiplication in R for vectors. Now, in vectors lecture, if you do not remember, go back and check. We have also learned about magnitude or norm of a vector. We have learned what is called unit vectors, right. Then we have learned what is the angle between two vectors, right. So, now I will implement those in R. So, the first thing that I will check is how to calculate the magnitude of a vector in R, right. So, what I will do, I will use norm function, which is a base function present in the base R. So, this norm function will take two argument at least, that is, one should be the vector for which you calculate the norm, and then you have to specify what type of norm. There are many types of norm. Actually, the magnitude that you calculate for a vector is called the second norm, norm 2. So, I have to specify that. So, what I am doing here in this line, I am saying that okay, you calculate norm, I am calling the norm function, and I am giving two inputs, two arguments. U is the vector for which I want to calculate the magnitude, and I am writing type is equal to 2. So, I am asking it to calculate the second norm, and it should assign that value, that will be a scalar value, to x, and in the next line I will print that value. So, let me execute both of them together. So, it says the second norm or magnitude of my vector u is 12.84 something. So, I have calculated the norm. Now, I want to calculate unit vector. If you remember, unit vector is nothing but dividing a vector by its magnitude, right. So, you have taken a vector and you are normalizing with respect to its magnitude, right. So, you will divide that vector by the second norm. So, that is what I will do simply. So, that is what I am doing here in this line. I am taking that u vector because I want to create a unit vector corresponding to u. So, I am taking that u vector and then dividing it by its magnitude. Just now I calculated the magnitude using the norm function. So, I am using the same norm function again, and I will get a new vector. Remember, unit vector is a vector, and I get a new vector that I assign to a variable called I. So, I will be my unit vector corresponding to u. So, I execute that, the I is created, but I want to see it. So, I write print I, and this is what I got. This is your unit vector corresponding to the vector u that we created earlier. So, just by simply dividing the norm, I got it. Now, I will go to the last operations for vectors that we have learned in our earlier lecture, is that angle between two vectors, right. So, let me explain what is angle, how we define the angle between two vectors. Usually, we know the relationship that the angle, if the angle is theta, angle between two vectors is theta, then the cos of that, cos theta is equal to dot product of these two vectors. Suppose the two vectors are v1 and v2. So, you take the dot product of this vector and divide by the product of the magnitude of v1 and magnitude of v2, right. So, that is we know is the definition of cos theta, when the theta is the angle between two vectors. So, I will use this formula to calculate cos theta, and then I will inverse it, so that I will use cos inverse to get the value of theta, fine. So, how I am doing it? It is a bit long, I will extend this. So, the first thing is I have to take the dot product of v1 and v2, two vectors. So, I am using two vector u and v. So, here I have taken it dot of u and v. So, I am using the dot function to calculate the dot product. Then I have to divide that by norm of these two vectors. So, the first thing I am taking in the denominator here, you see the division operator, and then I am dividing by norm of u and the second norm of v. They are multiplied by this multiplication operator. So, this whole thing will give me cos theta, but I want to know the angle in radians, right. So, I have to do cos inverse. So, that is why I will use a cos function, and that a cos function will invert this and will give me the angle which I assign to theta. Theta is the angle in radian, and in the next line I want to print that angle. So, it says the angle between these two vector u and v is 0.1308 in radians, right. So, it is very easy to do. Once I have the dot function and norm function, I can easily do that. That is all for vectors. There are many other things that you can play around with vectors, but we will not go into those. I am sticking to what we have discussed in our linear algebra classes. So, now I will move to matrices, and I will create first matrices. I will show how to create matrices, and then we will do matrix operation like multiplication, addition. Then we have to learn eigenvalue, how to calculate eigenvalue, eigenvectors, determinant of a matrix, and so on. So, let us start with creation of a matrix. How can I create a matrix? Here I will show 4 methods. The first one will use the matrix function, then the second one I will show you using cbind function, the third with rbind, and eventually I will show how to convert a data frame, if you know the table format of data, into matrix. Fine. So, let us start with first the matrix function. How the matrix function helps us? Matrix function will convert a vector into a matrix. So, I will give a vector as an input to this matrix function, and it will convert it into a matrix. So, let me explain with an example. So, in the first line here I am creating a vector d using C function, and I am saying start with 1, end at 10. So, it will start at 1 and then take 2, 3 and 4 up to 10, and it will create a vector d. So, let me execute that. So, now it has created. I can show you here, this is d, right, it is written d, and I have got those numbers, right. I can see also here in the console, if I write d, I can see the vector. Fine. Now, I want to convert this vector which has values from 1 to 10 into a matrix. That means, I have to break it in part and arrange them so that this one dimensional thing will become a two dimensional thing, right. So, that means, I have to tell the function who will do this job, the matrix function will do this job. That means, I have to tell matrix function that how many rows I want and how many columns I want. So, that is what I have done here. I am calling the matrix function, and the arguments are within the round bracket. The first argument is d, obviously the vector which is the input, and then I am telling how many rows and how many columns. Here I have said the n row, that is number of rows that I want in the new matrix is 2, and the number of column n col is equal to 5. 2 into 5 is 10, and I have 10 element, 10 numbers in my vector d. So, that means, I want to take these 10 numbers which are arranged in one dimension, and I want to break them to create 2 rows and 5 columns, right. Now, you can do it in 2 ways. So, you can start like this, right. You can arrange them the 1, 2, 3, 4, 5 and 6, 7, 8, 9, 10, something like that. So, that will be row wise, or you can start with 1, 2, 3, 4, 5, 6, something like that, that will be column wise. So, that is why the last argument here is by row, and I have said false. That means, I do not want row wise, I want column wise. Let me execute it, it will be more clear. I have created M. You can go to this environment pane, double click it, and you can see it here. See, originally I have 1, 2, 3, 4, so on up to 10. Now, I have broken that in 2 row 5 column, but not row wise. I have said row wise is equal to false, by row is false. So, that means, column wise, that is why it is taken 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Fine. So, that is how it has arranged. If I have said it equal to this equal to true, then if I execute it again, now let me see M. Now you see it is row wise 1, 2, 3, 4 up to 5 in the first row, and the rest of the data numbers are in the second row. This is how we actually can convert in a vector into a matrix, right. Now, let us one handy tool is to check that what we are doing, are we really creating matrix or not, is to call the class. Class will tell me what data class is this variable belongs to. So, I have already created M. So, let me check what is this data class, and it says it is a matrix or array, right. That is what we want. We want the vector to convert it into matrix or array. So, I have shown using matrix function, right. Now, I will use cbind function, column bind by column. What is that? So, here I want to combine vectors to create matrices. In the earlier case, I had one vector, break it down in matrices. Now, I have multiple vectors, I want to join them to create matrix, right. And in this case, these original vectors, if I use cbind, will be the columns of the new matrix. So, first let me create two vectors to explain this. So, I am creating two vectors D and E here in these two lines. It was very simple, I am using the C function, right. So, I have created two vectors D and E. Now, I want to combine them to create a matrix where this D and E will be columns. So, how I will do? I will call the cbind function, and the arguments are those vectors. So, the first vector will be D, the first column should be D, second column should be E. So, if I execute it, so I have created, let me print it, here it goes. So, you see the first column is D, second column is E, and the vector D is there arranged as a column and E is arranged as a column. So, I have created a new matrix M by binding column wise these two vectors. Now, I will use rbind, means I will bind vectors similarly, but row wise, right. The original vectors will become rows of the new matrix. So, to do that, I am creating again two vectors, and then I am joining them by calling the rbind function. Again here the arguments are D and E. So, D will be the first row, E will be the second row. So, I have created it, I can go to either print it or I can go and click on the environment pane on M, I should be able to see. Now, you see D and E are no more columns, they are rows. So, the first row is D vector originally 1, 2, 3 up to 10, and the second row of the new matrix is the E vector starting with 21 up to 30. So, this is how using cbind and rbind I can create new matrices by combining vectors. Now, come to the last thing of creating matrix. I want to convert a data frame, means you have read a data in a table format from a CSV file, or you have used inbuilt the data set, whatever you are getting, you have a data frame, right, a table. Now, you want to convert that into a matrix, and so that you will use matrix operation on that. So, for that what I will do, I will use a function called data.matrix. So, before doing that I need some data in table format, right, or data frame format. So, what I will do, I will use the BOD data set which is inbuilt in R. So, in your machine when you have installed R you have that. So, I will call that data and assign it to a new variable D. So, you can let me check the class of this D, what type of data is this, let me first read it. I have read the data. Now, I want to check the class. The class it is saying D is a data frame, right, and you can double click here also to see here it has time and demand, oxygen demand actually. So, you have this table, right. So, now I want to create a matrix out of this table. So, I want to convert this from data frame to matrix format. So, what I will do, I will call this data.matrix function. The argument should be this D, D is the data frame that I have, and the whole thing I will assign to a new matrix called M. So, if I execute that, and now if I check in the environment pane, you can easily see M has been created here, and let me double click it. You can see I have time and demand as the header, and I have the whole data as in a matrix format. But how do I know it is matrix? It looks like a table. So, I can check, I can go back and actually use that class option, class function to check the class of M now. So, let me check that, and it is saying it is an array, it is not a data frame, right. So, I have converted the data frame D, which is actually the BOD data, right, into a matrix M. Now, this matrix has this header, right, column names. Suppose you want to get rid of these column names, right. So, how can I do that? I can do this way, very simple. Column names of M, this is what I am writing here, that is what I am telling to R. Column names of M, M is the argument to this function M, and I am assigning null, null mean nothing, right, not 0, null mean nothing. I am assigning null to that. So, column names, call names of M, when I am writing M in the argument, column names function will extract the names of the header columns, right, of that matrix, and then it, as I am assigning null to them, all of them will become null, right. So, let me execute that and I will show you the effect. So, here I have executed. Now, I can print it. So, now you see you do not have any header, right, only the column numbers are there, or you can go to environment and you can see there is only V1, V2, because variable 1, variable 2, that is how it is saying, it does not have any column, specific column names. So, what I have done, I have learned till now how to create matrices. Now, I should go for matrix operations, right, like addition, multiplication, but before that I will go into what we have done for vector also, indexing issue, right, how to take a particular element of a matrix or a particular column or particular row of a matrix, right. So, if you look into matrix indexing, the system is like this. You should have a matrix name, and then in the square bracket you should have column number and row numbers. The first number is row number and the second number after comma is the column number. This is similar to vector. In vector we have used vector name, in square bracket I have the index or the element number position, right. Here in this case is a 2-dimensional matrix. So, that means I have two things I would say, right, mention. I have to mention the row number as well as the column number. So, the first number in that square bracket should be the row number, then comma, and then the column number. So, now suppose I have already created this M matrix, right, from BOD data set, and I want to take the data or the element of row 3, column 2. So, let me check. Row 3 is this one, right, and column 2 is this column, right. So, row 3 column 2 should be 19, right. So, let us do it. I want to print it. So, what I am doing in the print, I am giving argument M square bracket 3 2, that means 3 comma 2, that means 3 is the row number, 2 is the column number of whom, the M matrix, and I want to print that. So, if I print, yes, I get 19. Now, suppose I used to use the same indexing technique to not just get one value, but a whole column or whole row. I can also do that very easily. What I will do? So, suppose I want the first column. First column means I want this 1, 2, 3, 4, 5 up to 7, right, and I have to discard the second column. So, what I can say, okay, I want the first column of M. So, M followed by the square bracket, and I do not put any row numbers, because I know I want all the rows, right. So, I do not specify any row number. So, R will understand that I am asking it to give me all the rows data, and then after the comma I am specifying the column number. The column number is 1 and I want to print that. So, let me print it. Okay, somewhere I have missed the M while correcting. So, it has to be M. So, print M in the square bracket, no row number, and then the comma and the column number. Now, it should work. Okay, I have got the first column 1, 2, 3, 4, 5, 6, 7. Let us check in M. First column is 1, 2, 3, 4, 5, 6, 7. So, indexing is done. Now, we will go into the next operation called transposing a matrix. If you remember, we can transpose, right, we can convert row to column, column to row. It can be done very easily in R. To do that, we have a function called T, and if you call that function and give the matrix as a argument, in this case I will give M as a argument, I should be able to create the transpose of that. What I am doing in this line is that I am transposing M and creating and assigning that matrix to a new matrix called empty, and I will want to print it. So, let us do that. Now, you can see the original M matrix is how many rows we have? Let us open. We have 6 rows and 2 columns, right. Now, here in case of empty, which is transpose, it has 2 rows and 6 columns. So, we have transposed M. Fine. Now, I will do matrix addition. Matrix addition, to do that, I will create 2 new matrices which are smaller, so that we can easily perform some other analysis easily. So, I am creating a matrix 2 by 2 matrix, the M. So, what I am doing it, I am using the matrix function, that means I have to give a vector. So, the first argument here I am creating a vector using C function, and that vector will have values from 1 to 4, and I want to divide this vector into 2 by 2 matrix, and I want to make it row wise. Whereas, here I want to create a new matrix N, for which I am giving a vector which starts from 11 and ends at 14, and it is also 2 by 2, and I want by row equal to false, just like that I have given. I could have taken something else as an example. So, let me create these 2 matrices. I have created them. You can check here M and N, 2 by 2 matrices, right. Now, I will do all those vector operation on these 2. So, I want to do first thing is that I want to add these 2 matrices. I will add M and N. So, just like addition of 2 vectors, I will use the plus operator and I should be able to add them. So, here what I am doing, I am adding M plus N, I am adding M and N matrices, that those I made just now, and I am assigning to a variable called sum dot Mn. Obviously, that should also be a matrix, and I am printing it. So, let me do that. I have done it. So, I have added M and N, and I have got a new matrix sum dot Mn, which has these values 12, 15, 15, 18. Now, as I have done the summation, obviously, you can easily do scalar addition to a matrix. I have not shown that, that is not a issue. Now, I will go and show you matrix multiplication. Just like vector multiplication, matrix multiplication can be also of 2 types, right, like at least 2 types. One is the scalar, another one is the multiplication between 2 matrices that we have discussed in the lectures. So, first I will multiply the M matrix that I created by 2, a scalar, and then I will print it. So, I have multiplied it by 2 and then assigned that to Sm, and I have printed Sm here, and now I have got a new matrix 2, 4, 6, 8. Now, I want to do the complicated one, the matrix multiplication. 2 matrix has to be multiplied, right, and there is a rule to do that. You have to take the row and the column of the second one and do the multiplication. If you have forgotten, please go back and check the lecture on matrix multiplication to understand what I am saying, and then come back and look into this part of this video. So, if you want to perform matrix multiplication the way we have taught in that lecture, then you have to use this particular operator. You first put the percentage sign, then the star, and then the percentage sign. So, percentage, star, percentage, this is the operator for matrix multiplication. And what I want to do here, I want to do matrix multiplication between M and N. M and N we have created, and I will assign that to MM, a new matrix, and that is why I am using here that particular operator, percentage, star, percentage. Here I execute it and then I print it. So, I got 35, 41, 81, 95. You can go back and check the calculation using the M and N matrix, you will find you will get the same matrix. So, by multiplying these 2 matrices, I have got another matrix. Now, what will happen if you use the star symbol which is the add multiplication operator in R? You can do that, but that will give a different result. What it will perform? It will perform element by element multiplication. What do I mean by that? Let me open M and N. This is M matrix, this is N matrix. So, if I use M star N, then element by element multiplication will happen. That means, this 1 of M will get multiplied with 11 and that will remain in that position, that value. 2 will get multiplied with 13. So, index numbers of these two matrices are matching, right. When I am taking the first row first column value, I am multiplying it with the first row first column value of the second matrix. The second row second column value of the first matrix will be multiplied with second row second column value of the second matrix. So, this will element wise I will multiply. I will show you how what will happen if I do multiplication like that. So, here I am asking to print just using this star symbol, multiplication symbol. So, there should be element wise multiplication between M and N. Here you can see 11 and this one is 26. It is this one is 11 because 1 into 11 is 11. Then this one is 13 and the corresponding value here in the M is 2, 13 into 2 is 26. So, if you want to do element wise multiplication, then only you use this star symbol. Usually in the matrix multiplication requirement that we have in this data analysis course, we do not need that. We require the original multiplication that we have learned in the linear algebra class. In that case, remember you have to use this percentage star percentage operator to tell R that you want matrix multiplication, not element wise multiplication between the matrices. So, we have learned the matrix multiplication. Now, I will go to determinant and eigenvalues. How can I calculate the determinant of a matrix? In R, it is very easy. It has a determinant function, det function, which will take the matrix as an argument and it will output the determinant of that. So, I am printing it here in one line. So, I am saying print det of M, and if M is the matrix we already know. So, if I do that, I get minus 2. So, that is the determinant of M matrix, that is this matrix. You can manually do and check that. Now, I have done the determinant. Now, I will go to what we call eigenvalues and eigenvector, two very important quantities related to square matrices. So, luckily R has a inbuilt function to calculate both eigenvalues and eigenvectors. That function is called Eigen. It will take the matrix as an argument and it will return both eigenvalues and eigenvector. Let me first ask it to calculate the eigenvalues and eigenvector, and I will assign that whole data to this variable EV. This EV will store, this variable will store both the eigenvalues and eigenvector. Subsequently, I will separately collect the eigenvector and eigenvalue and print them. So, the first thing is I will run the eigen function. So, it has calculated both the eigenvalues and eigenvectors for M and has assigned the whole data to EV. Now, I want to collect the eigenvalues only. So, I am writing EV $ eigenvalues. So, values is an object of the output comes from the eigen function, and that values object has all the eigenvalues in it, and I want to fetch that from EV. So, I am using this $ symbol, right. So, I am saying give me the values that you are storing in value as values object in EV, and I will assign those things to values variable. Those are the eigenvalues. So, I do that and then I print them, and the eigenvalues are 5.37 and minus 0.37 and so on. So, now I can extract the eigenvectors in the same way. So, this the output of eigen function has an object called vectors, and I have stored the data in EV. So, I want EV to give me the vectors object. So, I am using EV, then the $ and then the vectors, and if I run this and I will assign that to this new variable vectors, done that. I want to print the vectors. Now you can see both the vectors. This is a 2-dimensional matrix, right? M is a 2-dimensional matrix. So it will have 2 eigenvalues, 2 eigenvectors. Check that it has 2 eigenvalues. So correspondingly there should be 2 eigenvectors. Okay. The first eigenvalue is 5.37. So its vector is here, the first column, minus 0.41, minus 0.9. So this is the eigenvector corresponding to the first eigenvalue, and next one is the second eigenvalue here, minus 0.37. So the next column in the vectors is the second eigenvector corresponding to the second eigenvalue. That is all for matrices. We have learned how to create vectors, how to create matrices and their operations, right? Addition, multiplication, indexing, all these issues. One important thing that we have learned in linear algebra class in this course is that we can use linear algebra to solve a system of linear equation. I will end this lecture with that topic. So, let me recapitulate how we solve a system of linear equation using linear algebra. Suppose you have told me that I have to solve these two equations, x plus y equal to 6 minus 3x plus y equal to 2. I have to solve these two. That means I have to get the value of x and y that will satisfy both these linear equation. So, how can I do that? I have to create some matrix and vectors. I have to create a coefficient matrix, usually we call it A. So, in this case the coefficient matrix will be 1 1 minus 3 1. 1 1 will be the first row, minus 3 1 will be the second row. Why? Because I have 1 into x plus 1 into y in this first equation. So, I have 1 1. In the second equation I have minus 3 into x plus 1 into y. So, that is why I have minus 3 and 1. So, this is the coefficient matrix. Then everything on the right hand side of the equal to sign should be in another vector. So, I have 6 and 2. So, that will be vector B, and I will should have 6 and 2. And the solution should be another vector, that is a capital X here, and it should have the unknown x and y. And I have to calculate this capital X vector. In other words, I have to calculate this small x and small y. How do we do that? We know this whole system of equation can be represented as A into x. A is the coefficient matrix, x is the unknown vector, and b is the right hand side vector, right. So, if I write A into x equal to b, then I can use linear algebra and I can get a solution of this. If I do something like that, the solution will be x, the vector, result vector will be equal to inverse of A, because I am taking A on the right hand side of this equal to sign, inverse of A into B. So, that means I have to do inversion of A. Now, this is what you do to solve a system of linear equation by linear algebra. Now, I will not do manually inversion and all these things to solve this problem. I will call a solver function, right, a function which will solve this problem for me. So, R has that function, it is called solve. So, it should take two arguments, A, the coefficient matrix, and the B vector, and then it will spit out this x, the solved values, right, solutions. So, let me start with creation of A and B. A is this matrix 1 1 minus 3 1. So, I am using rbind function. First I am creating the vector 1 1 here, and then I am creating the second vector minus 3 1, and I am joining them, I am stacking them row wise, I am binding them row wise using rbind. So, I should get A. I have got A, I can double click and check, okay. I have got 1 1 minus 3 1, I will use this A. I want to create the B vector should be 6 2 as I have said here. So, that is what I am doing here, I am using C function to create B. So, B has been created, let me print and see B, yes, B is 6 2. So, now I have got A and B, so now I can call solve function. So, I will do that. Here I am calling solve function of R, I am giving A and B as argument. So, the solve function will solve and spit out the vector x, which has the solution for x and y, and I am assigning that to a new variable called solution, sol. I have done that. Now, I want to print the solution, and the solution is 1 and 5. So, x equal to 1, y equal to 5. You can put these two value on those two equation and you will see this solution will satisfy both this equation. So, this is the way in one single line I can solve a system of linear equation. Now, when I was discussing matrices, I had discussed determinant, transpose, eigenvalues, how to do those things in R, right. But in the lectures of linear algebra, we have also studied how to invert a matrix, right, inversion of a matrix. And as I said here, to solve a linear equation, you have to do the inversion of a matrix. But today in lecture, I never discussed about inversion of a matrix, right, which we do very frequently in data analysis. So, how to do that? Actually, the solve function itself can do that. That is a good thing. So, how can I use the solve function to do that? This is very easy. The solve function has been written in such a way that, see, I have said I have to give two arguments, right. A is the coefficient matrix, B as the right hand side vector, right. Now, if you do not provide B, this function by default will consider B as a identity matrix. And if you remember that if I multiply any matrix with a identity matrix, then I get the same matrix. So, in this case it will multiply identity matrix with the inverse of A. So, it will give me inverse of A. So, if you want to get the inversion of a matrix, so what you simply do, you call the solve function, but only provide the matrix, do not provide the B vector. So, that is what I am doing here. I am calling solve, only providing A, not providing any B vector. So, it will only report me the inversion of A. So, if I run it and print it, this is the inversion of A inverse, right. So, A inverse is 0.25 minus 0.25 and so on. That is all for this lecture. We have learned how to use R for all those things that we have learned in linear algebra course in this course in the last week. Thank you for joining me today. Keep on learning. See you in the next video.